Welcome to the Bugs and Analysis session at SOSP 2015. My name is Brad Karp from University College London, and it's my pleasure to be chairing this session. We have three outstanding papers for you today. Our first speaker today is going to be Baris Kasikci. He's a final year PhD student in the Dependable Systems Lab at EPFL, advised by George Candea. And he will be on the job market this year. He's interested both in academic positions and in industrial lab positions. And I'm excited to hear about his work on helping developers figure out why their system failed in the wild.
People hear me well? Okay. Well, thank you, Brad, for the kind introduction and the first time ever accurate pronunciation of my last name in a conference. So today I'm going to present to you failure sketching, a technique for automated root cause diagnosis of in-production failures. This is joint work done with Cristiano Pereira and Gilles Pokam from Intel, my colleague Benjamin Schubert, and my advisor George Candea at EPFL. So developers need to understand the root cause of a failure in order to debug it. And traditionally, debugging is done iteratively. Users run their programs either on their own machines or in a data center, and whenever they encounter a failure, they can file a bug report. Or more realistically speaking, an automated report gets shipped back to the developers. Developers first try to understand the root cause of a failure by examining this report only. And when they're lucky, this works and they can fix the problem. However, things rarely go that way. After all, failure reports are usually static representations of the final state of the program right before the crash or a failure. And in particular, when programs are complex and the failure occurs as a result of complex interactions, it's harder for developers to understand such interactions. Therefore, developers try to reproduce the failure in-house, and generally many times, in order to better understand what statements and variables are relevant to the failure and which value they take in the failing executions in order to isolate the root cause. So this is an intensive process, and in general, reproducing failures and understanding their root causes is tricky. This happens because developers may not always be able to create the exact same conditions at user sites, or perhaps because the failures themselves are non-deterministic. Consequently, developers turn into detectives, relying on guesswork and ad hoc techniques to understand the root causes of bugs and fix them. So this is a problem, and there's a significant body of work that dealt with various aspects of this problem. And the body of work ranges all the way from collaborative approaches to approaches that do record replay and to ones that use special hardware support. I show some of these approaches on the slide, but we do really have a lot more of these in the paper. And we build upon all these approaches in our work. Our overarching goal in this project is to automate the labor-intensive detective work that developers have to go through manually. To do this, we pick from where existing systems left off, and in particular, our main contribution is a technique called failure sketching. Failure sketching complements in-house static analysis and in-production dynamic analysis to obtain failure sketches automatically and efficiently. Failure sketches accurately display the root causes of failures. And in the context of our work, we're talking about a statistical definition of a root cause. In particular, root causes are events that are primarily correlated with the failure. A key idea here is to do the time-consuming static analysis in-house and only do lightweight and efficient dynamic analysis in production to improve user experience while building failure sketches. So here's what a failure sketch looks like for a real failure in a real program. And aside from formatting, this is the output you obtain from our approach once it performs its analysis on the failure report and the source code. In this representation, time flows downward, and the steps in an execution are enumerated along that flow of time. The failure sketch shows statements from two threads that affect the failure, and the order of execution with respect to the enumerated steps. What the failure sketch shows in red is the most significant feature that differs between failing and successful executions. So now I'd like you to look at these representations for a few seconds to see if you can figure out the root cause of a failure in this program. So hopefully it's all clear, but coming back to the arrow between the statements in a box, this essentially says that only in failing executions, the free statement from thread 1 is executed before the mutex unlock statement in thread 2. On the other hand, in non-failing executions, this order of execution of statements never occurs. It turns out that in this case, and also in other cases according to our evaluation, these differences that are shown on the failure sketch point to the root causes of failures. A developer can fix the failure by introducing proper synchronization that eliminates the offending thread schedule. And this is exactly how the developers of this program fixed this bug, albeit 4 months after it was reported. Whereas if they had access to this failure sketch, we believe that fixing the bug would have taken a very short time. At this point, I'd like to acknowledge that failure sketching works well for cases where a failure can be automatically identified. However, for failures such as silent data corruption, which may be hard to detect automatically, failure sketching is less suitable. So how can we obtain failure sketches in the traditional model that I previously described? The basic idea that we have is that we can perform some intelligent and lightweight monitoring at multiple user sites and gather the results of such monitoring from failing and successful executions to perform some more analysis. Given that we monitor a large number of user executions, the likelihood of encountering failures will increase. We can then provide developers with the failure sketch, which has an obvious explanation of the root cause of a failure, and such an explanation obviates the need to reproduce the problem, and understanding the root cause becomes straightforward with no additional effort required other than reading the failure sketch. Since we automate detective work, developers do not need to act like detectives and can go back to building cool systems and applications. Okay, so in the rest of this talk, I'll first talk about the challenges of building failure sketches. Then I'll talk about the design of failure sketching in detail, and then I'll present some evaluation results before concluding my talk. So let's get started with the challenges associated with building failure sketches. The first challenge is building accurate failure sketches. Namely, it's hard to build failure sketches that exclude all irrelevant information while preserving all relevant information. If sketches are not accurate, developers would not want to look at them. The second challenge is the recurrence challenge. For failures that rarely recur, it's hard to gather enough execution information to be able to build failure sketches. The last challenge is the latency challenge, and it's related to the recurrence challenge. In other words, it's hard to build failure sketches only after a few recurrences of a failure. In particular, building a failure sketch has to take at most as much time as it would take for a developer to figure out the root cause of the failure by themselves. Okay, now that I briefly talked about the challenges of building failure sketches, I'll describe our system that we call GIST. We call our system GIST since it conveys developers to the gist of the failure. I'll first talk about the high-level design of GIST, and then I'll explain how each component in GIST works in detail using a running example. So we envision addressing the challenges of building failure sketches in the context of the usage model that I described. And now I'll explain how our proposed solution and architecture fits into that usage model. Our failure sketching system, GIST, has a client-server architecture that uses hybrid static dynamic analysis. The server side does compute-intensive static analysis, and the client side does lightweight dynamic monitoring. The server-side component takes as input the failure report from the users, this could be a core dump, and the source code of the program that's being debugged. These inputs are then fed into a static analyzer, which computes a static slice using these inputs. The static slice contains program statements that potentially affect the statement where the failure occurs. The client side of our approach gathers more control and data flow traces from both failing and successful executions by instrumenting programs in user sites by taking into account the slice that the static analyzer computed. We can then use these runtime traces to refine the static slices. And in the context of our work, refinement has a very special meaning. In particular, refinement removes from the slice statements that don't get executed during live executions and adds to the slice information such as access orderings. The static slice contains some excess statements and lacks ordering information because of the nature of static analysis that does not have access to live execution information. Finally, another server component uses the refined slices from both successful and failing executions to determine the differences between them and build a failure sketch. Okay, since we saw the high-level design of GIST, I will now delve into the details of the design of GIST. For this, we'll start with static analysis within GIST. Static analysis of GIST builds static backward slices with the primary goal of reducing overhead for subsequent dynamic analysis. A static backward slice will start from a certain statement of interest, in our case the failing statement, and will include statements that have read and write dependencies to the variables used in this statement of interest. Because GIST excludes statements that don't depend on the failing statement, it allows subsequent runtime tracking to be more efficient. GIST does interprocedural static analysis because dependencies of the failing statement can span function boundaries, and GIST identifies those dependencies to further improve the efficiency of ensuing dynamic analysis. The key takeaway from static analysis of GIST is that it helps following dynamic analysis monitor fewer events than it would otherwise require monitoring. In particular, static analysis helps GIST improve the cost of control flow tracking by a factor of 20. To better understand how static slicing works, I'll walk you through a simple example, and I'll continue using this example for explaining the rest of the operation of GIST. So in this example, let's consider the code snippets that show a cleanup function that prints some debug messages and deallocates the memory that was allocated for the state object S, and the display size function that prints some debug messages and displays the size of the state object S. There's, of course, other code, and in particular code that calls these functions, but they're irrelevant for the purposes of this example. It turns out that this program crashes when the log statement in the display size function accesses the size field of S, and I'll show you how GIST will help us determine the root cause of this failure. Now, in this first step, GIST computes the static backward slice starting from the failure point. And in our example, it removes the log function calls that are used to print function names upon entry to the function's cleanup and display size. This is because the failing operation, namely the loading of the size field of S, is in no way influenced by these statements. Of course, this is a simple example, but static analysis in GIST is capable of determining more complex dependencies, and I'd like to refer you to the paper for those details. Note that GIST will remove more statements in later stages, and we will come back to this example to explain that. So now that I explained how GIST performs static slicing, I'll talk about how both control flow tracking and data flow tracking helps with the refinement of these slices. So control flow tracking allows GIST to perform slice refinement by identifying statements that get executed in real executions and removing from the slice statements that don't get executed. So control flow tracking can be implemented in software in a relatively straightforward manner by tracking all the branches a program executes at runtime. And in fact, we experimented with this approach only to see that it has prohibitive overheads of up to 15x. Using hardware features can alleviate this overhead. And in particular, a recent feature from Intel processors, namely Intel PT, which is short for Intel Processor Trace, can record the branches executed by a program with lower overhead than software tracing. In our experiments, we've seen that full program tracking using Intel PT incurs runtime performance overheads of around 40%, which is much lower than what a software-based approach has. However, it is still quite not suitable for in-production use. GIST, on the other hand, combines static analysis and hardware-based control flow tracking to further reduce the overhead to negligible levels. A key insight here is that GIST will do control flow tracking only for the portion of the slice that it monitors at runtime in order to reduce the overhead to these negligible levels. So let's go back to our running example for which GIST previously computed a static slice. In our example, when GIST performs control flow tracking for multiple executions in production, it determines that the log line that prints the address of the pointer S in the cleanup function is never executed. This is expected because when a program runs in production, verbose debugging messages are generally disabled in order to not incur high overheads. At this point, I'd like to emphasize the synergy between static analysis and control flow tracking. Note that both of these techniques collectively help narrow down the set of statements related to a given failure, thereby shortening the sketch. Static analysis removes from the slice statements that are not related to the failing statement, and control flow tracking removes from the slice statements that don't get executed at runtime. Okay, so this was control flow tracking in action. For data flow tracking, GIST tracks values that are read and written by the statements in the static slice. During data flow tracking, GIST also tracks the total order of statements accessing the memory and augments failure sketches with this information to help developers better reason about bugs for which understanding ordering can be crucial, such as concurrency bugs. I'd like to stress that this is a very important component of GIST. GIST needs to track this total order because Intel PT, which is the technology we use to track control flow, does not provide this information. For tracking the data flow in a program, GIST relies on hardware watch points. For a given memory access that GIST tracks, GIST inserts a hardware watch point at the address of the variable it tracks, and then GIST tracks which threads access this variable and also the order of these accesses. Note that watch points are a scarce resource, so if GIST runs out of watch points while performing data flow tracking, it will distribute monitoring tasks across multiple clients. The key takeaway here is that data flow tracking allows GIST to have precise ordering information, thereby increasing the accuracy of failure sketches substantially. So coming back to our example, for data flow tracking, GIST places a hardware watch point at the address of the state object S, and it monitors the values of S as well as the order of accesses to S across multiple threads. So let's have a closer look at what happens when GIST does this data flow tracking for our example. Now, GIST will determine that in successful executions, that is the ones that don't end up with a sec fault, the log statement that accesses the size field of S in the display size function executes before the delete statement in the cleanup function. And these statements execute in different threads. Whereas if the cleanup code executes before the access to the size field of S, the program will fail with a sec fault. Okay. We saw how GIST performs control and data flow tracking. So let's now look at how it monitors multiple user executions to statistically isolate the root causes of failures. The way this works is GIST looks for what is called failure predictors. A good failure predictor will portend a failure with high probability. And in particular, GIST searches in refined slices for failure predicting access patterns such as data races, atomicity violations, or rare paths that the program executes. As an example, consider data races, which are at the heart of many concurrency problems. A data race occurs when multiple threads access a shared memory location. At least one of these accesses is a write, and synchronization operations do not enforce an order among these accesses. So given that definition, there are 3 data race patterns that can be failure predictors, and we show them on the slide. So given a shared memory location X, these patterns are a write-write data race, a write-read data race, and a read-write data race. GIST then identifies these failure predictors across multiple executions, and it uses statistical techniques to identify the root causes of failures. We show in our evaluation that these failure predictors are indeed what developers identify as failure root causes and end up fixing. Coming back to our example, GIST goes ahead and monitors multiple user executions, and it determines that indeed failing executions exhibit the same failing ordering, and whereas successful executions don't exhibit this ordering. GIST then computes precision and recall for these failure predictors and ranks them in order to determine that the access pattern to S, where S is first deleted and then referenced, is the best predictor of failure. Recall that this is one of the data race patterns that GIST seeks in executions that it monitors, namely the read after write data race pattern. In our paper, there are more details regarding the statistical techniques and the ranking that GIST uses, and I'd like to encourage you to have a look at those. So before I move on, I'd like to reiterate that the strength of GIST comes from the combination of static program analysis and cooperative dynamic analysis. And I will actually show in a short while how various components of GIST contribute towards GIST accuracy and thereby its effectiveness. So we've seen the design details of GIST, and now I'll talk about some of the experimental results we obtained using GIST. In particular, in this section, we will answer the following questions. Do failure sketches GIST built help developers perform root cause diagnosis? Is GIST efficient, and is it accurate? So when evaluating GIST, we analyze client-side executions in the lab as opposed to employing real users. And this is because CPUs with Intel PT support are still scarce, having become available only recently. In the future, we plan to use a real-world deployment to evaluate GIST. Altogether, we gathered execution information from more than 1,000 simulated user endpoints and evaluated GIST using real-world systems such as Apache, SQLite, Memcached, and Transmission, among others. To answer the question of whether failure sketches help developers do root cause diagnosis, we manually analyzed the failure sketches of 11 failures for which we had GIST built failure sketches. We determined that the root causes identified by GIST indeed point to the root causes of the failures that developers ended up eliminating. An interesting result is that failure sketches that GIST built reduce the number of source statements that are necessary to be looked at in order to detect the failure root causes to an average of 7. Considering that this number is several orders of magnitude smaller than the size of the programs in our evaluation, we believe that GIST was useful. Overall, we conclude that GIST was able to build failure sketches that point developers to the root causes of failures. We then evaluated the efficiency of GIST by measuring the runtime performance overhead that it imposes on the executions that it monitors. This graph shows the average runtime performance overhead of GIST across all runs as a function of the tracked slice size. In the context of static slice tracking, the overhead incurred on the client side increases monotonically with the number of statements that GIST tracks from the static slice, and this is what this graph shows. Overall, GIST has low average overhead of always below 5%, and the overhead values have very small variance. Therefore, we do not show these on this graph. We also measured the accuracy of GIST as compared to ideal failure sketches that we built by hand. Intuitively, the more a failure sketch built by GIST resembles an ideal failure sketch, the more accurate it is. To compute accuracy, we determine whether the sketches GIST built contains statements from the ideal failure sketch and whether the order of these statements is correct. Ideal failure sketches contain a minimal number of control and data flow elements, whereas sketches built by GIST can contain extra elements. To obtain accuracy measurements, we first measured accuracy when just using static slicing. We then enabled control flow tracking and remeasured. And finally, we enabled also data flow tracking and remeasured. We observed that GIST has a high average accuracy of 96%, and we also observed that the amount of individual contribution varies substantially from one program to the next, which means that neither of these techniques would achieve high accuracy for all the programs on its own, and so they're all necessary if you want high accuracy across a broad spectrum of software. I'd like to also note that although the contribution of static analysis seems to be less than that of dynamic data and control flow tracking, static analysis is key in doing less dynamic monitoring, thereby reducing the overhead. In conclusion, we presented a new technique called failure sketching and the use case that we're targeting, in which we gather data from users' executions using a combination of static analysis and hardware monitoring in order to build failure sketches. A failure sketch is a succinct and high-level representation that shows the differences of failing executions and successful executions in a way to clearly display the root causes of failures. Failure sketching can build accurate failure sketches efficiently, and failure sketches can improve developer productivity. Feel free to visit our project website for more resources, such as related source code. And most of the authors are here at SOSP, so feel free to talk more to us in the poster session and afterwards, and reach out to us with your questions and comments. With that, I'd like to conclude my talk, and I would be happy to answer your questions.
Okay, so Tom Ping from UT San Antonio. So I have a few questions. The first question is, from my understanding, you have to rely on the statistical analysis to find out, those statements, they may have problems. Yeah?
I couldn't hear you. To find out? You said to find out what?
Yeah, you have to rely on statistical analysis to find out that those statements, they may cause problems first.
Okay, yeah.
Yeah? You have to do that.
You don't have to rely on them, but because we rely on them, we end up having less overhead in ensuing dynamic analysis. You could do all of this in runtime tracking, so you don't have to do it. But if you do it, we've shown that you have better overhead results. And also better accuracy results, because I showed the interplay between static analysis and dynamic tracking. Right? Both of them collectively help you get rid of statements that are irrelevant. So it contributes both towards accuracy and performance.
Okay. So actually, that's related to my second question. So my second question is, suppose you only have, normally like the hardware only have 4 registers, hardware watch points.
Yes.
So because like if you don't use statistical analysis, it looks like you cannot like monitor all these like accesses.
That's true. So that's one of the benefits of using static analysis. So because we narrow down the set of statements to look at runtime, and we actually start looking at a few statements, a few statements at a time, we're able to economically use our budget of hardware watch points.
Yes.
But we can still run out of them. And as I pointed out, when we run out of them, we will start looking at multiple clients and multiple executions to compensate for this lack of hardware watch points.
Oh, okay. Sorry, German. Okay.
Hi, Joe Tuchek, HP Labs. So I was just wondering if you had a comparison with the accuracy if you did a full dynamic backward slice without any, shortcuts. I mean, very expensive, absolutely, but.
So the question you're asking is, if we were to do full dynamic slicing, what would happen to accuracy?
Yes.
Right? So if you do full, so that basically the reason why accuracy may still suffer in the case of full dynamic analysis is because if you're looking at the number of statements that are larger than is necessary for understanding the root cause of the failure, in other words, you have extraneous statements in the sketch that you built, your accuracy will still suffer. But in the general case, I think our approach can do, at best, as good as the full dynamic slicing. So dynamic slicing would be like an upper limit of accuracy for us in the general case. That's true.
Bill Tetzloff, IBM Research. Do I get the order right that when you have a failure and you know it's in a fragment of code somewhere, that's the point that you start to look at that same fragment of code as it executes correctly?
That's true. So we will have to, in correctly executing executions, we'll have to see the same code point basically to do the correct execution monitoring. That's correct.
And then one more short one. Roughly how far back temporally can you go with a root cause and detection of the failure?
How far?
Temporally, like 5 minutes between something.
Okay, so with regards to the approach, there's no real limit with respect to how far you can go. Of course, the farther you go in the size of the static slice that you monitor, you will have an associated overhead with dynamic tracking.
All right, let's thank the speaker one more time, please.